In this video, we'll solve the coin change problem with dynamic programming. In the previous video, we saw that the greedy algorithm wouldn't give an optimal solution for all coin systems. The greedy algorithm made us first pick the 20-cent coin to make 30 cents. We only focused on each moment, and because we can't take things back, we end up with 11 coins at the end. Now that we know about dynamic programming, we are able to consider previous solutions to get the optimal solution, which will let us choose only two 15-cent coins. At a high level, if we want to make 30 cents with this algorithm, we will look at the optimal solution for 29 cents, 15 cents, and 10 cents. And once we get to 29 cents, 15 cents, or 10 cents, we only need to add one more coin, either the 1 cent, the 5 cent, or the 20-cent coin, respectively. So if you know the minimum number of coins to make 29, 15, and 10 cents, then just pick the case with the smallest amount of coins and add 1, which is the last coin that you'll add to your total, and that will be your answer to make 30 cents. This will prevent us from picking a non-optimal coin like in our greedy algorithm. The detail that's left for us to figure out is how to get those optimal solutions for each of the remaining amounts. We learned two approaches in the Fibonacci number problem, a recursive top-down approach and the iterative bottom-up approach. In this video, we will use the iterative bottom-up approach to solve the coin change problem. We will write a function that can get the minimum coin count with any given set of coins. So the function will have to take in an array that represents the coin system and the total amount we want to make change for. For example, if there are 1, 15, and 20 cents in the system, and we have to make 30 cents out of it, the input will be the array 1, 15, 20 for the coins and 30 for the amount. We are going to find the minimum number of coins for each amount from 0 to 30 and write them down in an array. Then we will return the value for 30. So we will create an array with a size of amount plus 1 and call it A. And after we find the value for the last index, we will return it. Let's start filling up the array from the beginning. The amount 0 should always return 0 because we don't need any coins to make 0 cents, so we set A of 0 to 0. Then we move on to the next index and find a way to make 1 cent. This slot needs to hold the minimum count to make the amount 1. If we pick the number of coins to make the amount 1, the last coin we chose can be 1, 15, or 20. But because the amount 1 is smaller than 15 and 20, we won't bother considering them. So the only and best option is to pick 1 cent as the only coin, which is a single coin. So we insert the value 1 on index 1. Let's go to the next one and think about making 2 cents. We have 3 options for the last coin, 1, 15, and 20, but we will only consider the coin that is smaller than the amount 2. So we will again assume that we picked a 1 cent coin. So the minimum count for index 2 would be 2 because we picked 2 1 cent coins. It is pretty obvious to us why the minimum coin count is 2, but we need to be able to express that in code. Currently, the amount is 2, and the last one that was chosen was a 1 cent coin, which means we need to fill in 1 more cent. So we look up A of 1 to check the minimum coins for the amount 1, which is 1, and add 1 to 1 and write that down at index 2. The reason we add 1 is because we are adding the last coin at this round. And this is going to repeat until we reach index 15 because we can only pick the 1 cent coin until then. Currently, we are looping each index for A and filling it up. So we will use a for loop to loop through A, and the amount will be represented with I. Then for each index, we are looping through the coins array, but we are only considering the coins that are smaller than the current amount, I. So we use an if statement saying if coins j is smaller or equal to I, and this is where we write the code that assigns the minimum coin count to A of I. So how do we define what goes in A of I? Let's see what happens once we reach 15. Now this time, according to the if statement we just wrote, we have two options, the 1 cent and the 15-cent coin. If the last coin is 1 cent, we have 14 cents more to go, so we check A of 14, which is 14, and we add 1 for this round's pick, which gives us 15 coins. If we express that in code, it would be A of I minus coin of J plus 1. But if we pick the 15-cent coin, 15 minus 15 would be 0. And if we check A of 0, which is 0, so 0 plus 1 would be 1. A of 15 could either be 15 or 1. We should write down the smaller count, so 1 would be the final count. Inside this loop, where we loop through the coins array, we can assign the minimum count by saying, get the minimum between the current count, which is A of I, and the count we get if we pick this coin. So as we loop through the coins array, A of I will end up with the smallest A of I because it will be replaced with the smaller value. But if we want this to work starting from the first loop of the coin array, we need to initialize the array with a higher number. The highest possible value for the elements of A would be amount plus 1, because there is no way we can pick 31 coins or more to make 30. So we will fill A with amount plus 1 right after we create it. So this loop will keep going on after 15, assigning each minimum coin count to A of I until we reach the end of the loop. Now we just have to return A of amount. But before we do that, we have to return minus 1 if there is no possible cases for the given amount. If there are no solutions, A of amount will be left as the initial value, which is amount plus 1. So we return -1 if A amount is larger than 30. For example, if the coins array was 15, 20, instead of 1, 15, 20, there is no possible solutions for the amount from 1 to 14 because the if statement cannot be satisfied, which would leave them as 31. This is the solution for the iterative bottom-up approach of the coin change problem. If the number of coins is m and the amount is n, the time complexity would be O of m times n, because we are iterating through the amount, and inside that loop, we are iterating through the number of coins. Unlike the Fibonacci number approach, we need to store the results for each amount because we need to look up the previous indices. For the Fibonacci number problem, we only had to check the previous two values. That's why we could just use two variables instead of a whole array. However, in the coin change problem, we don't know which index we would need in the future, so we need to hold on to all of them. That's why the space complexity is O of n, where n is the amount. That was the coin change problem explained and solved with dynamic programming.